Hello, folks. How y'all doing? We're covering section 3.1 today. Let's go ahead and get started. We can start with the definition. The n by n matrix In, whose column vectors are the standard basis vectors, is called an identity matrix. So, for example, I2 has the E1 vector in the first column and the E2 vector in the second column. And I3 has the E1 vector in the first column, the E2 vector in the second column, the E3 vector in the third column. In general, we have ones going down the diagonals, no matter how many entries we have, and zeros everywhere else. Everywhere else in the matrix. So I'll quickly try to write out I6. Looks like this. Like so. One's going down diagonal, everything else is zeros. And we have one of these for each size of n. So I2, I3, I4, all the way up. There is an I1, which just looks like that, but it's not very useful. And so in general, we'll start with I2 when we're talking about the identity matrix. There is technically an I1, though. We see that a matrix is invertible if we can find another matrix so that when we multiply them together, A times B is an identity matrix. If so, the matrix B is called the inverse of A, and it's written as A to the minus 1 power. So that's the idea, that if I have a matrix and another matrix that when I combine them together, I get the identity matrix, then they are considered to be inverses of each other. So as an example, let's say that A is the matrix that rotates vectors in VR2 counterclockwise by 90. I'm sorry. A is the matrix that rotates vectors clockwise by 90, and B is the matrix that rotates vectors counterclockwise by 90. And we're going to construct these and check that when we multiply them together, they cancel each other out and give us the identity matrix back. So we're going to start with the standard vectors. E1 is the unit vector in the x direction. E2 is the unit vector in the y direction. When we rotate by 90 degrees clockwise, A times E1, that's clockwise, so that should be pointing downwards. And A times E2 should be pointing to the right. And so the transformed version of E1 and E2 should be 1 unit down is 0 and negative 1. 1 unit to the right is 1, 0. Counterclockwise, when we rotate E1 counterclockwise, it's now pointing upwards. And when we rotate E2 counterclockwise, it's now pointing to the left. And so B should be the matrix. Pointing straight up is 0, 1. Pointing to the left is negative 1, 0. And so these are the transformation matrices for A and B. What happens when we multiply them together? All right, we'll apply the column row rule to this. So we will compare up 0, negative 1 with 0, negative 1. And 1, 0 with 1, 0. All right, 0, -1 times 0 is just 0, 0. 0, -1 times -1 is 0, +1. 1, 0 times 1 is 1, 0. 1, 0 times 0 is 0, 0. When we add these together, we get 1, 0, 0, 1, and that, in fact, is I2, which is what we're going to check. And so when we combine them together, E1 goes back to E1 and E2 goes back to E2. And that should make sense if we rotate 90 degrees clockwise and we rotate 90 degrees counterclockwise. They cancel out. And they put our E1 back where it should be and our E2 back where it should be. All right. Can we use this definition to find the inverse of A? We can, but using the definition is messy and hard. I want to show you what would be involved. And I'm going to talk through the process, but we're not going to work through the calculations. Using the definition, there is some matrix. This is my inverse matrix here. And when I multiply A times A inverse, that's using the column row rule. So we get 3, 1 times AB and -2, -1 times CD. Add them together. This should be the identity matrix I2. But this is saying that 3A minus 2C is 1, which is this equation here. And 3B minus 2D is 0. That's this equation here. A minus C is 0. And B minus D is 1. That's that equation there. And that gives us a 4x4 system of equations. When we row reduce this, we get this system here that says A is equal to 1, B is -2, C is 1, and D is -3. And so that tells us that A inverse is the matrix 1, -2, 1, -3. That works, but it's slow and it's tedious because we started with a 2x2 matrix and ended up having to row reduce a 4x4 matrix. The matrix squared in size. And so if we move on to a next size, let's look at example 3. We want to show that this matrix is invertible. Well, if we used a definition, we would have to row reduce a 9x9 matrix. Sorry about that. And a 9x9 matrix would be just very, very time consuming. And so we're going to learn a trick to shorten the row reduction process. The process for finding the inverse of the matrix A, which we're going to write A inverse, again, that's the inverse, involves augmenting the matrix with the standard basis vectors and row reducing. That is, instead of augmenting with a single column, I'm going to augment with all of my standard basis vectors for whatever this system is. And we're going to row reduce and find out what happens to E1 and E2 and E3 in this process. And that, once we put this in reduced echelon form, and we do have to use reduced echelon form for this, that we need the ones in this position so that we end up with the identity matrix over here instead of over here. The identity matrix is moved from the right side to the left side, and we end up with the inverse. All right. So this is the matrix that we were looking at in example 3. And let's just verify these calculations here. All right. So this is a matrix. We're going to augment this matrix with an identity matrix. And we're going to put this into reduced echelon form. All right. Since I already have a 1 here, what I'm going to do is I'm going to switch row 1 and row 3 and put the 1 up in the top corner. That means I have to switch row 1 and row 3 on this side also. All right. Now I'm going to cancel this 2. I'm going to take row 2 minus 2 times row 1. And I'm going to cancel this negative 3. I'm going to take row 3 plus 3 times row 1. See how this works, okay? So 2 minus 2 is 0. 5 minus 8 is negative 3. Negative 4 plus 6 is 2. 0, this should have been 0, 0, 1, sorry. I've switched rows here. 0 minus 0 is still 0. 1 minus 0 is still 1. 0 minus 2 is negative 2. All right. 3 plus 3 is 0. Negative 7 plus 12 is 5. 6 plus negative 9 is negative 3. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 3 is 3. All right. So now I need to change this 5. 5 and negative 3 don't play too nicely, but we can use a linear combination here. We'll take 5 times row 2 plus 3 times row 3. All right, 15 and negative 15 goes away. This is going to be negative 9 plus 10 is going to be 1. That's convenient because we already get a 1 here. This is going to be 3. This is going to be 5. And this is going to be 9 plus negative 10. This will be negative 1. All right. Okay. So now this is echelon form, but we need reduced echelon form. We'll start with the right column and change these 2 entries. So this is going to be row 2 minus 2 times row 3, and row 1 plus 3 times row 3. All right, so 1, 4, negative 3, and 3 is 0. 0 plus 9 is 9. 0 plus 15 is 15. 1 plus negative 3 is negative 2. All right, 0. Negative 3. 2 plus negative 2 is 0. 0 plus negative 6 is negative 6. 1 plus negative 10 is negative 9. Negative 2 plus positive 2 is 0. All right. We're going to divide row 2 by negative 3. And that's going to get us 1, 4, 0, 9, 15, negative 2, 0, 1, 0, 2, 3, 0, 0, 0, 1, 3, 5, negative 1. And finally, we have to get rid of this 4. So let's do that. Row 1 minus 4 times row 2. 9 minus 8 is going to be 1. 15 minus 12 is going to be 3. Negative 2 minus 0 is still negative 2. 0, 1, 0, 2, 3, 0, 0, 0, 1, 3, 5, negative 1. All right. And that gives us a solution. The inverse matrix is 1, 3, negative 2, 2, 3, 0, 3, 5, negative 1. All right. Let's go ahead and move on. Here we go. Sorry. Move on. There we go. As these examples show, we can find the inverse of a matrix by creating an augmented matrix with the identity on the right side and reducing it so that the identity is on the left side. When we do that, we get the inverse. In order for this to work, in order to get the identity on the left side, A has to contain in pivot positions. That is, the reduced echelon form has to look like 1's going the down diagonal, which means A has a pivot position in every row and every column. Now, this tells us that if A is an invertible matrix, then the columns of A because there's a pivot position in every row, the columns of A span Rn, and because there's a pivot position in every column, they are also linearly independent. So invertible matrices combine the idea of being a spanning set and being a linearly independent set. These two concepts we studied on test 1. Now when we combine them, we get invertibility. Theorem before that, theorem 24, says that if we have an invertible matrix, then any equation of the form AX equals B is consistent, and there is a unique solution. AX equals to the inverse matrix times B. I'll explain what's going on in theorem 24 on the next slide. Let's take a look at what's going on. I have some system of equations AX equals B, and we know that A is invertible. All right, so that tells us that I have an invertible matrix. So if I'm going to multiply both sides by A inverse, then this gives me A inverse times AX. Remember, we defined matrix multiplication so that we can drop the parentheses, but A inverse times A is the identity matrix. And the identity matrix times a vector is just a vector. And so X is equal to A inverse B, but that's exactly what the theorem says, is that we can solve a system by multiplying both sides by the inverse of the matrix. Okay. This is something that you do in regular algebra. If you want to find 3x equals 9, you can multiply both sides by 1/3. And on this side, the 1/3 and the 3 cancel, and we just get x equals 3. Turns out that that rule works for matrices if the matrix is invertible. So let's move on and try an example using this. So let's solve this system of equations. So this is the system where A is -3, -7, 6, 2, 5, 4, 1, 4, -3. But the instructions say to use the previous example because we've seen this matrix already. I'm going to back up a few slides now. That's this matrix right here. And we already know the inverse is 1, 3, -2, 2, 3, 0, 3, 5, -1. So let's go ahead and put that information in here. A inverse is 1, 3, -2, 2, 3, 0, 3, 5, -1. If we have the inverse, then we can solve this system of equations by just combining the inverse with the column vector B. So we get 1, 3, -2, 2, 3, 0, 3, 5, -1. This is A inverse. Combine this with 2, -1, -1. This is our B. All right. 2 goes with the first column, so this is going to be 2 times 1, 2, 3 plus -1 times 3, 3, 5 plus -1 times -2, 0, and -1. And when we add those together, that's going to be 2, 4, 6 minus 3, 3, 5 plus 2, 0, 1. And that's going to be 4 minus 3 is 1, 1, 2. And so x is equal to 1, y is equal to 1, z is equal to 2. And we should be able to check that. We get, let's see, -3 minus 7 is -10. -10 plus 12 is 2. That equation checks. 2 plus 5 is 7. 7 minus 8 is -1, so that checks. 1 plus 4 is 5. 5 minus 6 is -1, so that checks. And so this illusion checks. Let's move on. We have an even shorter cut for 2x2 matrices. If I have a 2x2 matrix, then I can calculate the inverse of the matrix by taking the main diagonal, A and D, and switching their positions. These become D and A. And then take the other diagonal, the minor diagonal, which is B and C, and they don't switch positions, they change signs. And then at the end, we multiply by this number here, 1 over AD minus BC. And this number here has a name. It's called the determinant. And next time, we're going to look at more properties that the determinant has. But for right now, it's a part of our shortcut for 2x2 matrices. Switch the positions on the main diagonal, switch the signs on the other diagonal, multiply by 1 over the determinant. Okay? So let's try some examples here. Find the inverse of these two matrices. So A inverse is going to be 1 over the determinant. So AD is 2 times 2 minus BC is 5 times 1. On the main diagonal, they change positions, but since they're the same, we can't really tell anything has happened. On the other diagonal, we change signs, so -5 and -1. This is 1 over -1, which is just -1. And so we get -2, +5, +1, and -2. Let's try one here. The determinant is 3 times 6 minus 2 times 8. So that's 18 minus 16. So the denominator here is 2, 1/2. The main diagonal changes places. So 3 and 6 switch places, and 2 and 8 switch signs. And so when we multiply this by 1/2, we get 3, -1, -4, and 3/2. And that's the inverse of that matrix. Very fast process, no row reduction at all. But you do have to learn the process. Okay? This value, AD minus BC, is called the determinant of the matrix. What we'll kind of focus on next time is what does the determinant tell us about the matrix? Can we find the determinant for a matrix that's larger than 2 by 2? Can we leverage this for larger matrices as well? And the answer is yes, we can do that. All right, we're going to wrap up with a definition and a theorem. The rank of a matrix is just the number of pivot positions in a matrix. That's all it is. So if I have a 4 by 4 matrix, it could have a rank of 4, but it could have a smaller rank. It could have a rank of 3 or a rank of 2 or a rank of 1. Could even have a rank of 0 if the matrix is all zeros. So the rank of a matrix can't be larger than the size of the matrix, but it can be smaller. It's just the number of pivot positions in the matrix. And here's our theorem. All of these statements are equivalent. That is, if any statement on the list is true, all of these are true. They all mean the same thing. First one says that A is invertible. Back when we look at theorem 25, we saw that if a matrix is invertible, that meant that we had to have a pivot in every row and every column. And since it has a pivot in every column, the columns are linearly independent. Since it has a pivot in every row, the columns span or end. Normally, these two things are not the same. But because the matrix is square, then having a pivot in every row means that we have a pivot in every column. That is, if I have a matrix that's square and I have a pivot in every row, then I run out of rows at exactly the same time that I run out of columns, and so I must also have a pivot in every column. These two statements usually are not the same, but because this is a theorem about square matrices, they are the same for this special case. All right. The rank of A is n. The rank is just the number of pivot positions. That means that whatever n is, we have that many pivot positions. The homogeneous equation has only the trivial solution, and we know that's true because there are no free variables. Because we have a pivot in every column, so we cannot have any free variables. And we know that the equation is consistent for all b in Rn. To be inconsistent, we need a row that looks like this. But we can't have a row that looks like this because we know that we have a pivot in every row because the matrix is invertible. And so this can't happen. And therefore, the equation is consistent for all b. All of these statements mean the same thing when we are talking about square matrices. All right. Last theorem. This is called the shoes and socks rule and the cancellation rule. And I'm going to hide myself here so we can see the slide. Shoes and socks rule says that if A is an invertible matrix and B is also an invertible matrix, then their combination is invertible. That is, if I can undo A and I can undo B, then I can undo the combination AB. But the undoing is in reverse order. The inverse of AB isn't A inverse B inverse, it's B inverse A inverse. We call this the shoes and socks rule to help you remember it. In the morning, you put on your socks and then you put on your shoes. When you undo that process in the evening, you have to remove your shoes first and then you remove your socks second. So the order that we put things on in the morning is reversed from the order that we take them off at night. And the matrices observe that same property. The inverse of AB exists, but we have to invert them in the reverse order to calculate the inverse. In the cancellation rule, we saw earlier that cancellation usually doesn't work for matrices. But if A is invertible, it can be canceled. Invertible matrices can be canceled. Excuse me. But only if they're on the same side of a product. That is, either AB and AC with the A's both on the left, or BA and CA with the A's both on the right. If we have this situation, where the A is on the left in one situation, one side, and A is on the right on the other side, we still cannot cancel the A's, even if they're invertible. So it's a partial cancellation rule. Matrix cancellation is more fragile than cancellation of numbers. Invertible matrices can be canceled, but they have to be on the same side for the cancellation to work. And that wraps things up for today. Thanks for putting up with me. I will see you guys next time. Whoops. There we go. Y'all take care. I'll see you around. Bye.